The category non-Newtonian fluid is pseudoplastic fluid. If I can write the Ostwald equation again, that is tau is equal to mu apparent into du by dy plus b. In the pseudoplastic equation, and you know that the mu apparent will be, also we can write mu apparent will be a into du by dy raised to power n minus 1. So in the pseudoplastic, this b value will be equal to 0 and n will be less than 1. In pseudoplastic, this b will be 0 and n is equal to 1. So we can say if this n is 1, then this term n minus 1 is negative. N minus 1 is negative, and in place of du by dy, if I write d theta by dt, okay, we will confirm it with, we will understand it with d theta by dt. So I can say if n is negative, as the flow is continuing, as the d theta by dt increasing, if you increase this d theta by dt, as this n is, this term n minus 1 is negative, then the apparent viscosity will decrease. This is the important concept, that in the pseudoplastic, the apparent viscosity will decrease with the flow. Apparent viscosity will decrease with the flow. So you can write here that in the pseudoplastic, your apparent viscosity is decreasing with d theta by dt. If the viscosity is decreasing with the flow, if the viscosity is decreasing, we can say that flow will become easy. Right? If the viscosity is decreasing, then the flow will become easy after some time, because viscosity is decreasing. And if the viscosity is decreasing, this is also known as, aka is also known as, these type of fluid is also known as shear thinning fluid. Shear thinning fluid. As we already discussed, that dilatant fluids are the shear thickening fluid, because in that viscosity is increasing, but here viscosity is decreasing, so they are known as shear thinning fluid. So I can say that a fluid is said to be a pseudoplastic fluid if its apparent viscosity is decreasing with the flow, or you can say if its apparent viscosity is decreasing with the rate of shear strain or with the your rate of angular deformation. So this is known as pseudoplastic fluid. So if I wrote what is the that example of pseudoplastic fluid, then the example of pseudoplastic fluid is your milk, blood. These are the example of your pseudoplastic fluid. So if you draw the diagram here, draw the curve or graph here between, if I draw the graph between shear stress and d theta by dt, this is shear stress versus d theta by dt. Then the shear stress versus d theta by dt is, as this is negative, so this graph will look like this, in which the slope is decreasing at each and every point. This shape of parabola or any curve is the shape in which slope is decreasing at each and every point. So this is the pseudoplastic curve. This is pseudoplastic curve. And if you draw the apparent viscosity versus d theta by dt graph, if I draw the apparent viscosity versus, this is apparent viscosity versus d theta by dt graph, if we draw, then it will like this. Apparent viscosity is decreasing with d theta by dt. Apparent viscosity is decreasing with d theta by dt. So the next, this is the pseudoplastic fluid. right? Next type is, third one is, if we can say that the third type of fluid is your Bingham plastic fluid, right? The third one is your Bingham plastic fluid. This is also a non-Newtonian fluid, right? So let us discuss what is the Bingham plastic fluid. So if I write the Ostwald equation again, then tau is equal to mu apparent into du by dy, and mu apparent will look like, this is equal to a into d theta by dt raised to power n minus 1. In the Bingham plastic, the condition is this B is not equal to 0. This B is here, right? B is here plus B. This B is not equal to 0, and this is equal to, B will be not equal to 0, or you can say B will be equal to some shear stress tau naught, and n will be equal to 1, right? N will be equal to 1. So if this n will be equal to 1, right? So you can write here that this n will be equal to 1, so this will be 1 minus 1 0, so the mu apparent will be equal to A, or it will be equal to mu only, dynamic viscosity only, right? This will be equal to dynamic viscosity only, right? So what this shows, if I write the equation again here, then Ostwald equation will look like tau is equal to tau naught plus mu into du by dy. Now just pay attention here. Right. Tau is equal to tau naught plus mu into du by dy. Right. So if I say that in this case the apparent viscosity will be equal to the dynamic viscosity, and if you can see from here, if in this case let us suppose that du by dy will be, or you can say this du, if in this equation you will put, if du by dy will be equal to 0, du by dy is 0, it means that shear stress will be equal to tau naught. Right? Now what does this means? Now just pay attention. They will ask this concept in your interview or some other technical rounds. You can face this question. What does this mean? It means that when the shear stress which you apply, this is the tau, the shear stress you apply when this is less than or equal to tau naught, this means that you are applying a shear stress of value tau naught, but du by dy is 0 or d theta by dt is 0. It means the fluid is not flowing. It means that you are applying a shear stress of the value tau naught, but the fluid is not flowing. The fluid is at rest. So if you apply a shear stress of the value less than equal to tau naught, then in that case the fluid is not flowing, the fluid is at rest. If you remember the previous discussion, the first basic definition of fluid, we say that the fluid is that substance which can flow however the small shear stress you apply. Any small shear stress you can apply, the fluid must flow. That is the basic definition of the fluid, right? So just remember one thing, that definition is valid for the Newtonian fluids. Or you can say that the Bingham plastic or this fluid is not satisfying the basic basic definition of fluid, right? So that's why we can say this is not a Newtonian fluid. That equation is valid, that statement of the fluid is valid for the Newtonian fluid, not for non-Newtonian fluid, right? You can see here that you are applying a shear stress tau naught, but fluid is not flowing. So this is not a Newtonian fluid. This is a fluid, but it is non-Newtonian fluid. So that definition of the fluid, that it has to flow, however the small shear stress you can apply, that is valid for the Newtonian fluids, right? If somebody asks whether the Bingham plastic is a fluid or not, Bingham plastic is a fluid but not Newtonian fluid. It is non-Newtonian fluid, right? So this is the case. So if you can see that this is the straight line equation, this is a straight line equation. So if I put the graph between shear stress and d theta by dt, if I put the graph between shear stress versus d theta by dt, shear stress versus d theta by dt, then the graph is a straight line, but it will start after some tau naught. It is a straight line, this is a straight line, but it will start from some point, and this value is tau naught. So from 0 to tau naught stress, there is no flow, there is no angular deformation. After that it will be a straight line. So this is the this is known as, this tau naught is known as, this tau naught is known as yield stress of the fluid. This is known as yield stress of the fluid. Yield stress of the fluid, right? And in this case, as this is the viscosity only, so it is not a function of d theta by dt. So if you plot a graph, small graph I am plotting here, if you plot a graph between, if you plot a graph between viscosity and d theta by dt for Bingham plastic, then it will be a straight horizontal line. It will be a straight horizontal line. It will not depend upon the flow. It will not depend upon the d theta by dt. And if you want an example for this, the example will be toothpaste, right? If you remember that to flow the toothpaste, to make it out from that toothpaste tube, you have to apply some minimum stress, right? If you apply a very small stress, then that toothpaste will not flow. After some minimum stress only it can flow. So toothpaste is the example of this. Then you can say jelly is also an example. Jelly is also an example. Jam which you are used to eat, right? That jam like. So that jam is also an example of Bingham plastic. Any cream is also an example of Bingham plastic. So this is the fluid which is which will take, or which will need some minimum stress, minimum shear stress to flow, right? Now if I can write these are the three example of the non-Newtonian fluids in which viscosity is not a function of time, right? Now if I can say that, let us discuss about rheopatic or thixotropic. Rheopatic or thixotropic fluid. We will discuss these two types of fluid in which viscosity is a function of time. In these, viscosity is a function of time. So we can say that we can write the Ostwald equation, that is tau is equal to mu apparent into du by dy plus b. Mu apparent into du by dy plus b, or you can write it as a into du by dy raised to power n plus b. So in rheopatic and thixotropic, in both of them b is not equal to 0. In both of them b is not equal to 0. and n value of n can be less than 1 or can be greater than 1. Value of n can be less than 1 and can be greater than 1. So these are the rheopatic and thixotropic fluid in which some minimum amount of stress is required for the flow. So for example, you can write here, for example, paint. Paint is the example, or that printer ink. Printer ink is also example of time dependent viscosity fluid or rheopatic or thixotropic fluid. So these are the example of your rheopatic and thixotropic. So we can say that in this case as this value of n is not 0 or not 1, we can say n value is not 1. So in these cases the apparent viscosity will depend upon, in this case the viscosity will depend upon both time and d theta by dt. It will depend upon both time and d theta by dt. So in this, viscosity is a function of time, right? So if I write here that how the graph of them will see, if I rub this just to draw the graph of time dependent and time independent viscosity fluids, right? We will show it with the help of a graph. If let us say if this is the viscosity, in this case this is the viscosity mu, right? Apparent viscosity or any viscosity, and in the horizontal axis we have time. In this we have time, right? So the time independent fluids will be of like this. This is time independent, like your dilatant, Bingham plastic, pseudoplastic, and time dependent will look like this, right? In which the viscosity is either increasing with time or the viscosity is decreasing with time, right? So the fluid in which the viscosity is increasing with the time is rheopatic fluid. This is rheopatic fluid, and in which viscosity is decreasing with the time, it is thixotropic fluid, right? You need not to go in detail about these. Just for the objective type you have to remember this, that in rheopatic viscosity is increasing with the time, and for thixotropic viscosity is decreasing with time, right? So if I show all of them in one class or in one graph, if I want to show all of them, then how we can represent all of the fluids, Newtonian, non-Newtonian, dilatant, pseudoplastic, Bingham plastic, right, thixotropic and rheopatic in one graph. So let us make a generalized graph for all of them between shear stress and the angular deformation rate. So if I draw here, the y-axis will show this is shear stress versus d theta by dt graph. Shear stress versus d theta by dt graph. We know that this x-axis will represent ideal fluid. We will show one by one. This is ideal fluid. This straight line will represent Newtonian fluid. This will represent Newtonian fluid. Now no Newtonian fluid, first one is the dilatant. So this type of graph, this type of fluid, this type of graph is dilatant, in which n value is greater than 1. Newtonian means n is equal to 1. This is pseudoplastic, in which n value less than 1. Shear thinning fluid, you can say shear thinning fluid. This is Bingham plastic, in which n value is 1 and this is tau naught or B, this is tau naught, and two more fluids are there which we can say it is your rheopatic or the thixotropic. They are like, this is thixotropic, is look like this. This is thixotropic and this graph is rheopatic. Rheopatic means n is greater than 1 and thixotropic means n is less than 1. Right, so these are the different types of graph, thixotropic or rheopatic, and Newtonian and non-Newtonian can be represented by this. You have to remember this so that you will be able to solve all the question come from the types of fluid chapter, or you will get a match the flowing type, so you will be easily you can understand it and you can easily able to solve these kind of things. So this is all about the types of fluid. Stop. Start. Now let us discuss the important topic of your fluid mechanics, or we can say the basics of fluid mechanics, that is the surface tension of liquid. It is also a property. Let us discuss this surface tension. The surface tension, as the name suggests, it is the tension force on the surface, right? And this surface tension arises due to cohesion and adhesion. We will discuss it. So this surface tension is arising because of the unbalanced cohesive and adhesive forces, right? We know that the cohesive forces are the intermolecular force of attraction between the same fluid or between the same particle, right? And because of this cohesive forces, this cohesion will enable the liquid to resist tensile stress, right? If you apply a tensile stress on the liquid, then because of this cohesive property, they can resist that tensile stress, right? And the adhesive forces are the intermolecular force of attraction between the different molecules, right? And because of this adhesion enables two different liquids to adhere to each other. If two different liquids are in contact, or you can say one liquid and one solid is in contact, or one liquid and air is in contact, or some gases is in contact with each other, then because of this adhesive forces, they are enables to adhere these two different liquids, right? And because of these unbalanced adhesive and cohesive forces, we can say there arise the surface tension. Now let us discuss. Suppose this is the interface, right? Below this we have liquid, let us say any liquid, water is there, and above of this interface we have air. Here we have air and here we have liquid. Now let us take one molecule, we'll take one liquid particle, let us say A, right? There is a liquid particle here A. This liquid particle is sufficiently below in this liquid. This A molecule is surrounded by the same molecules or same particle of the liquid. It will surrounded by the liquid particles, and these liquid particles will exert the intermolecular force of attraction, right? Suppose let us say this is the sphere of influence, right? This is the sphere of influence over which this cohesive forces are acting. Let us say this particle is A, right? I can write A here, right? So different molecules, different particles of the fluid which are surrounding this molecule A, they are exerting the attractive forces which is the cohesive forces, right? This is the sphere of influence. So we can say that this molecule A is in equilibrium, or we can say that the net attractive force, because of the surrounded particles, net cohesive force on this A will be 0. Net cohesive force on this particle A will be 0. Right. Now let us take one more particle. We will take this particle here. This particle here. Let us say this is the particle B. Right. This particle B is near to the interface, not at the interface. This is near to the interface. This particle B is surrounded by the same liquid particle, but we can say this B particle has less liquid particle above and more particles below, right? So we can say that if we will say that this B particle is exerted force like this, in the downward one particle will be here, one particle will be here, right? So these particles are exerting the cohesive force of attraction, and there are some particles here which will cause the attractive force, but as the particle above this B particle is less, so the less attractive force will be in the upward direction. So on this B particle, the net cohesive force is downward. Net cohesive force is downward because there are very less particle above this, so the force of attraction above is less, so the net force will be in the downward direction. And the magnitude of this net cohesive force will be maximum when we will take the particle on the interface. If I take the particle on the interface, let us say C, on the C particle, this is the sphere of influence, right? This is a sphere of influence. So below this particle, we have the liquid particle which will exert the cohesive forces of attraction, right? Like this. And above this interface, there are air particles, and these air particles will apply the adhesive force on this particle C. Adhesive force on this particle C. Because here air particle is applying the intermolecular force of attraction on the liquid particle, so it is the adhesive force. And because of this unbalanced cohesive and adhesive forces, the net force will be in the downward direction, because cohesive force is always greater than the adhesive force generally, so the net force will be in the downward direction, right? So the net force will be in the downward direction. So we can say that the particles which are on the interface, will feel, or there is a tensile force is existing on these surface particles, right? On each and every particle, one tensile force will be acting in the downward direction, right? So we can say that these interface particles of this liquid, we can say they seems to be in the layer, right? We can say that it is feel that the surface particles are always in the stretched condition. Some force is there to stretch it, some force is existing there to stretch it, so they are like a stretched membrane. We can say there will be a layer or a stretched membrane. This is a stretched membrane, and this stretched membrane of the surface, it can resist a small tensile force. If you apply a small tensile force, they can easily resist it, and this phenomenon is known as surface tension. This phenomena is known as surface tension. So this interface will be like a stretched membrane. Stretched membrane. And because of this stretched membrane, they can resist the tensile stress or tensile force, and this phenomenon is known as surface tension, right? And surface tension is a line force. We can say that surface tension is a line force, and mathematically it can represent like surface tension we can represent with the letter sigma, right? Sigma, surface tension is sigma, which is equal to, mathematically it is equal to force per unit length. Force per unit length. And we can say that this length is drawn, this length over which you are calculating, this length is drawn, this length over which you want to calculate the surface tension, this length is drawn through surface and at the normal to the line in plane of surface, in the plane of surface. This is the plane of surface, this is the line of the plane of surface, the line which is in this direction. If I draw a line in this direction, inside the board, so this is the length which we have to take into account to calculate the surface tension. And we can say that surface tension is because of unbalanced cohesive, and just make very clear point here, unbalanced cohesive and adhesive forces, right? Not only because of cohesive, it is because of both cohesive and adhesive forces. If you remember about viscosity, the viscosity is mainly because of cohesive, but surface tension is because of both cohesive and adhesive forces. Hence most important point is surface tension is not a property of liquid. Surface tension is not a property of liquid. Surface tension is, if I write here that the surface tension is a binary property. Surface tension is a binary property which depend upon the interface. Which depend upon interface, right? It is a binary property. Surface tension will depend upon both air and liquid. If here we have some solid, suppose one liquid is in contact with some wood or some iron, then surface tension will be different. If water is in contact with mercury, then surface tension is different. If water is in contact with the air, surface tension will be different, because in this both adhesive and cohesive forces are playing an important role. So it is a binary property, not a property of a single fluid. No, it is a binary property, right? You just make it very clear. They may ask this concept in the interview, that whether the surface tension is a property of fluid. No, surface tension is not a property of fluid. It is a binary property of the interface. It will depend that on both sides of the interface which fluid or solid or air is present, right? If you change any of these two, then the surface tension will change, right? So it is the binary property. And surface tension will depend upon temperature. Surface tension will depend upon temperature also. Surface tension is a function of temperature, because we know that if you increase the temperature, then cohesive forces will decrease. cohesive forces will decrease, and if cohesive forces will decrease, then surface tension will decrease. Surface tension will decrease, right? Because if cohesive forces will decrease, then this unbalanced force will decrease, so surface tension will decrease. So it is a function of temperature. And if we talk about the critical point, at critical point is that point where liquid will directly converting into gas without absorbing any heat. We know from the basic concept of thermodynamics. So at critical point your surface tension is 0, because at critical point there is no interface. There is no interface because liquid directly vanish into gas or vapor, right? Liquid directly vanish into vapor. Liquid will directly convert it into vapor without taking any heat. So you cannot demarcate a boundary, you cannot demarcate a interface. So if there is no interface, there will be no surface tension, right? So this is the basic concept of surface tension, and surface tension is the cause of surface tension is the unbalanced cohesive and adhesive forces. Both will play an important role. Now, if I can say that because this surface is always under a tensile force, you will feel that a tensile force is acting, something will be there which can just stretch it in the downward direction. So we can say that if you want to take any molecule from inside to the surface, then work has to be done on each molecule arriving at the surface. If any molecule is arriving at the surface, then you have to do some work. You have to do some work against the action of an inward force. Against this inward force, you have to do some work to put a molecule from here to at the surface, right? Thus we can say that mechanical work is performed. You have to perform a mechanical work in creating a free surface, right? So if I write, it means that some conclusions, if I write here, if I write some conclusions or some important points, then the first one is that mechanical work has to be done. Mechanical work has to be done to, if we can say the mechanical work has to be done to create free surface. If you want to create a free surface, then mechanical work has to be done. Or if you want to increase the surface area, right, then you have to perform a mechanical work. So mechanical work has to be done to either you want to increase the surface area or you want to create a free surface. Second, right? So that a surface which you want to create, or if you want to increase that, it will require a mechanical energy for its formation, right? You have to give some mechanical energy for its formation against this inward force, and we can say that this mechanical energy is stored in the form of free surface energy, right? This mechanical energy is stored. This mechanical energy is stored in form of, we can say, free surface energy. This can be stored in the form of free surface energy, right? And we can say that any system, because there is a free energy stored in this free surface, then any system which wants to be in equilibrium, every system wants to be in equilibrium, then in the equilibrium every system wants that its potential energy or its surface energy must be minimum, right? So all the free surface will try to minimize its surface energy or try to minimize its potential energy. So we can say that any liquid will try to adjust its shape, right? If you left any liquid, it will try to adjust its shape so that its surface energy will be minimum. So we can say that for a given volume, that's why we can say that for a given volume, the sphere has minimum surface area. For a given volume, the sphere has the minimum surface area, right? And we want that the liquid will have the minimum surface energy. The minimum surface energy will be possible if the surface area will be minimum. So for a given volume, the sphere will have minimum surface area. So sphere surface will be having minimum surface energy. That's why all the bubbles, liquid drop, and everything will try to take the shape of sphere. That's why if you see that if the rain is coming, or if you drop a liquid or water drop, then it will take the shape of, after some time it will take a shape of sphere. That is the main reason, because they wants to minimize its surface energy, right? So we can say that free surface energy, if some free surface energy is stored in the surface or in the interface, then the free surface energy implies the existence of a tensile force. It will implies that a tensile force is existing in the surface, and that surface is under stretched condition due to this tensile force, right? So this is the basic concept of the surface tension. And because of the surface tension and because of the surface energy, that every drop, every bubble, every liquid drop, water drop will try to take the shape of a sphere, right? This is a concept of surface tension. Stop.